In this video, we solve problem 6.2.4 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to find a general solution for the given differential equation using x as the independent variable. It is a linear constant coefficient homogeneous equation. This particular problem appeared on quiz number 4 in the spring 2021 semester. And this is one of the questions that was used to assess whether students understood the method of solving or method for solving homogeneous linear differential equations with constant coefficients. So since that's the type of equation we have, we're going to start by letting y equal e to the mx, because if I take derivatives of exponentials, I get other exponentials. For the right exponentials, this is just going to be the right combination of constants that are multiplying exponentials that get added together, and all the constants cancel out and we get 0. So we just have to find the value of m that would cause this to be a solution to that. In order to find those values of m, we need to compute the derivatives. This is third order, so we need first, second, and third derivatives. And then we need to substitute y and y's derivatives into the differential equation. And then we'll have, after simplification, a characteristic equation involving m. So let's do that. And let y equal e to the mx. The derivative of e to the mx is e to the mx times the derivative of the inside, which is m. Take the derivative again, you get another m by the chain rule. Take derivative again, you get another m. And then we substitute into the differential equation. But when we do, it no longer becomes, or it's no longer a differential equation, so I'm just going to call it an equation. The third derivative is this m cubed times e to the mx, and we're subtracting the second derivative and subtracting 26 times the first derivative. And we've got 24, and we're subtracting 24 times the original function, and that's going to give us 0. So we've got this algebraic equation that must be satisfied if y equals e to the mx is a solution to this equation. So the values of m that cause this equation to be true are the values of m that cause y equals e to the mx to be a solution of that differential equation. So we just need to solve this equation for m, and then we'll have the form of our solutions. So first we factor out the exponential. We get this. Now the exponential is never 0. So we have this here. And that's called the characteristic equation of the differential equation. Well, we want to solve this in whatever way we know how. The easiest way to solve a cubic polynomial equation is to factor that cubic polynomial. But this doesn't factor easily. So what I would recommend is you use possible rational roots. It doesn't factor by grouping easily. So we'll just start listing some possible values of n that happen to be rational. Actually, all the possible rational roots of this equation. And then we'll choose values from our list and try to see which ones will give us that 0 that we want. The possible rational roots of this polynomial equation are given or can be found using the factors of the constant term, and then dividing the factors of the constant term by the factors of the leading coefficient. And the factors, or the constant term is negative 24, and the leading coefficient is an implied 1. So we want factors of 24, so plus and minus 1 and plus and minus 24 would work. Plus and minus 2 and plus and minus 12. Plus and minus 3 and plus and minus 8, plus and minus 4 and plus and minus 6, and I think that's it. 5 doesn't work, and we end up going to 6, which is already on the list. And then we'll divide all of those by plus and minus 1, but that doesn't really do anything. So we've got all these possibilities. 1, 2, 3, 4, 6, 8, 12, and 24 are the positive possibilities. And then the same numbers but negative are the negative possible rational roots. Now I know we've got a lot of numbers on that list. You've got 1, 2, 3, 4, 5, 6, 7, 8, 16 possibilities. but it's better than infinitely many. And we know we shouldn't try m equals 5 because there's no way that m equals 5 will work, just for example. So this shortens the list of possible roots to 16 possible rational roots of this equation. So you can pick a value for m. Just ask yourself, what do you think will work? If I plug in m equals 1, I'd have 1 minus 1, so that'd be 0, and then a negative 26 and a negative 24. So I'd have negative 50. So 1 is not going to work. Let's see. What about negative 1? Would that work? Let's try it. I have negative 1. If I cube that, if I just substitute negative 1 into this equation, let's see what happens. I've got a negative 1. Negative 1 squared is 1 times negative 1. Then negative 26 times negative 1 is positive 26 minus 24. And this is going to give me a negative 26 plus the 26. That gives me a 0. So that's great. So that means m equals negative 1 is a root of the polynomial. And that means that m plus 1 is a factor of the polynomial. So what we did was we listed possible rational roots. And then you just try values from the list until you can find one that gives you a 0. A 0 of a polynomial and a root of a polynomial are the same thing. So okay. All right, try m values until you find a root. We found one. I got kind of lucky. It just, the first one, I did this in my head and it didn't work, but then I said, oh, I think negative 1 might work. And so we got that. So what that means is m plus 1 is a factor of this polynomial. So this cubic polynomial can be written as m plus 1 times some quadratic polynomial, which I'll call q of m. To find q of m, I have to take this polynomial and just divide out the m plus 1. So we've got m cubed minus m squared minus 26m minus 24 is equal to m plus 1 times q for some second degree polynomial q. And that's equivalent to saying that q is equal to this. If I take both sides of the equation and I divide by m plus 1, I get this. And that's nice. So it tells me exactly how I can find q. I just do this division. So we're going to find q of m by dividing. You can use long division if you want. I'm choosing to use synthetic division. It's super fast. Okay, so the way synthetic division works, you set this factor in the denominator equal to 0 and solve for m. In this case, it's a negative 1. It's the root that corresponds to that factor, provided that the leading coefficient of the factor itself is 1. And then you list the coefficients of the polynomial in the numerator over here. So we've got a 1, a negative 1, a negative 26, and a negative 24. Then we bring the 1 down. Then you multiply, and then you add, and multiply, and then add, and then multiply, and then add. And you should get a 0 there because m equals negative 1 was supposed to be a root, and that means the remainder should be 0. Okay, so I did get a 0, and that means these are the coefficients of the quadratic polynomial that's remaining. So we have a 1m squared minus 2m minus 24 as our q. So this divided by this is equal to this. So that means this cubic polynomial is m plus 1 times that quadratic polynomial. So now we want to use that to completely factor, the characteristic equation, or characteristic polynomial if you prefer. So we have m plus 1 times m squared minus 2m minus 24 equals 0. And then I ask myself, does that factor? Are there two numbers out there that multiply to give me negative 24 that add to negative 2? Well, if the product is negative, that means they have to have opposite signs. So I'm looking for a difference of 2 in a product of 24. So 6 and 4 should work. If the 6 is negative and the 4 is positive, negative 6 plus 4 would be negative 2, and negative 6 times 4 would be negative 24. So those are the numbers that go here and here. And our characteristic polynomial has been factored. So now we want to use these factors to find m1, m2, and m3. So we just set each factor equal to 0 and solve for m. So m1 is equal to negative 1, m2 is equal to 6, and m3 is equal to negative 4. Okay, so we've got 3 distinct real roots. So those lead to 3 linearly independent solutions. y1 equals e to the m1x, y2 is equal to e to the m2x, and y3 equals e to the m3x. And again, that's because we didn't have any repeated roots or any complex conjugate roots. So this will be e to the negative 1x, and this will be e to the 6x, and the last one will be e to the negative 4x. And then the general solution is y equals c1y1 plus c2y2 plus c3y3. So that's c1 times e to the negative x plus c2 times e to the 6x plus c3 times e to the negative 4x on the interval from negative infinity to infinity. And that is the general solution, and I believe that's what we were asked for. Yep, that's it. So you let y equal e to the mx, you take the derivatives, you substitute, got a polynomial equation, you factor it however you can. So if you can use factoring by grouping, do it. If you can't, start with possible rational roots. Once you find a root, use the root to find a factor. Once you find a factor, divide out the factor. Usually I use synthetic division. Once you divide out the factor, you're left with a polynomial. If that's quadratic, you can always use the quadratic formula. If it's not quadratic, you could do the possible rational roots again. And if it's factorable, then it's really easy to just factor and go from there. So you want to get your characteristic polynomial factored as much as possible, find the corresponding values of m, and once you find the m values, the roots of that polynomial equation, use those to find the corresponding solutions. Once you have the solutions, it's a third order equation. The general solution is c1y1 plus c2y2 plus c3y3.